very impressed by Rob's dedications and his passions on this topic. So I'm sure today we'll have very thoughtful discussions. So for today's presentation, so feel free to raise your hand, ask questions, interrupt Rob if you have any questions or need any clarifications. Okay, so with that, Rob, so please go ahead.
All right. Thanks everyone for showing up. I'm going to start introducing our topic here, which is an extreme near field EMI, EMC pre and post compliance test bed. I'll kind of go into what some of these terms mean here. This is our overall outline, background, the basics, our test bed, principles of operation, modeling of the test bed, experimental results, conclusion, and future works. So we'll start off with a little bit of background and a few acronyms that I'm going to come at you immediately with because they're used all the time in this field. Continuous wave, just all that is a sine wave. It's a sine wave that I use in my model. Electromagnetic interference, EMI. I think you're all familiar with that. Electromagnetic compatibility is essentially, think of you have EMI from item A and EMI from item B. Well, when you put item A and B together, are they compatible? Are they going to create issues amongst each other and be able to function normally? We talk about E field and H field. That's the H field is in particular what we're going to really be looking at, the magnetic field, which is current induced. There's also the voltage induced, which is E field, and then everything that I'm testing, as we'll refer to as the victim, or trying to see if it's immune or susceptible to what I test, is called a device center test. Sorry, I don't know if that was a question. Question? All right, in 1967, when they had a plane inadvertently release some missiles on board a aircraft carrier, USS Forrestal. 134 sailors were killed, and they narrowed it down to electromagnetic interference actually coupling to the system that detonated or sent signal to the weapons. So it can obviously have very devastating effects. As time went on, in 1996, they started having actual medical deaths, coupling of EMI to, say, pacemakers, ventilators, lots of issues in the civilian world as well, including, say, Mercedes-Benz or other car manufacturers as they began to onboard complex chips. They weren't really taking into consideration the vulnerability of those chips to nearby EMI. EMI can also obviously be caused by radar, high voltage, and in some cases, when these new cars with the computerized chips were driving by airports, all of a sudden their windows would start rolling up and down from the air traffic control radar, right? Or their automatic brakes would start pumping. So it was very dangerous, and they started to realize, okay, we need to do something about this. And I was exposed to it actually at a very early age, about 18 years old. This is a picture of my father here in his famous tower at Coral Beach while he's lifeguarding. I still actually lifeguard there, and he's since retired, but it was interesting. He came in and he was telling me, Rob, I can't hear my radio. I pick up my phone, it's just this piercing sound on my phone. What is going on? So I started to kind of look around, and we finally pinpointed, what's this god-awful thing that's hanging from the top of your tower? Where did that come from? So someone basically overnight came in, it happened during the night, obviously after shifts. They installed a full system that was actually looking at tidal wave movements, and it actually connected back to my alma mater at UC San Diego through Scripps. So it's kind of interesting. They obviously didn't consider any electromagnetic compatibility, no EMC concern at all. They threw all these different items together. They started having issues and bleeding over into systems, even emergency broadcast systems bandwidth. So needless to say, the FCC found out about it, and it was fully removed, and my dad was happy.
Rob, you can see those
yeah,
all over the coast.
Right. Well, now I'm sure that they've actually passed and tested 461G and made some of those considerations. But when they initially hodgepodged all that together, not so much.
Yeah, so you just handled that and plugged it in there.
Yeah, well, I guarantee it was R&D, research going on there. So how does this really apply also to our field in the Navy, more specifically some of the DDGs here? If you look at 1991, 10% of that ship was actually electrical, right? So you had 75 megawatts, but only 7.5 of it was actually electrical. Anything that's electrical can put off EMI. Okay, so 2016, now you're almost 10 times as much power, and guess what? It's all electrical power now. It's all electrical, which means all EMI all over the place in the ship. In fact, the Zoom Wall class, interesting, I have very close friends and family that were going to be stationed on that ship, and due to EMI and a lot of other issues, it spends most of the time in port because of a lot of EMI type issues. So, and other issues, but EMI is certainly one of them. The DDGX is planned on going to 150, almost twice the power, 150 megawatts, and once again, 100% electrical power. So EMI is going to be a major issue. On top of that, they're pushing the type of power that is on these destroyers to be a wide bandgap type of silicon carbide devices that, as Professor Weatherford will beg you about for years, it continues to be a major issue. The frequency continues to increase of what it's resonating at. This is a plot of radiated emission versus frequency. And as you can see, the silicon carbide on the green curve, but it is shifting to the right. It's shifting it into higher and higher frequencies. And so is the Navy, are mill standards actually capturing some of these problems that are going to be extremely important and all over the new ships as they're using this technology? And this is just a little example here, a little picture of a power electronics circuit from Professor Reed's class. You can see here some radiated emissions coming off and coupling to, for instance, a gate drive board, coupling to it and creating lots of issues. So anything that's very adjacent to it, as you compact everything down the circuitry, you don't have that much free space to attenuate some of the energy. So it's a direct coupling in the near field to a lot of these devices that are critical. And so how does Mill Standard approach this then? They must be looking at what do we do about this? Well, they go about it from two different perspectives, either limiting the source, as in cutting down the radiated emissions, or protecting the victim. You can also think of as hardening the susceptible devices. And so for instance, this is a plot right here of dB microvolts per meter. So obviously electric field versus frequency. And they actually go up to relatively high frequencies, up to 100 gig. And they do almost all this in the far field. The problem is the way that a lot of the people pass Bill Standard 461G is, okay, we just need to make sure that our radiated emissions is not at this level. So let's just put a little Faraday shield over top of it, house it with a chassis that's grounded. And yeah, as far as 461G is concerned, problem solved. But now you have basically a miniature reverberation chamber. Now all that energy is traveling around, bouncing off the walls, coupling to all the inner circuitry. Does Mill Standard test for that? Absolutely not. It's only looking at the boundary of that housing. And so that is certainly a vulnerability that is not seen through typical radiated emissions testing. Now the radiated susceptibility side, this is the protecting the victim side. As you can see here, they actually do go relatively near field, 5 centimeters, so they're kind of right up on the device, similar to this, but we're actually much closer. But they're only going from 10 hertz to 100 kilohertz. Remember the power electronic up to 400 megahertz we were talking about? That's not covered. Now, granted, there's bulk current injections, other types of testing in Mill Standard, because they realize there's voids in this. In fact, I know a lot of people in my career are currently in the process of rewriting a lot of these Mill Standards because they're just simply outdated. 461G was put out in 2015, right? And as the power electronics, everything advances faster and faster and faster, the whole EMI threat is dynamic. It's changing every day. So, and then this is just kind of getting into, I mentioned near field, far field. The test probes that I'm using are all near field. I go straight, we're talking like 0.1 millimeters, right up on the device under test. I'm injecting it directly into the equipment to see what its vulnerabilities. In the RS testing, radiated susceptibility testing, it is in the near field, but it's only at like 5 to 7 centimeters. So they're not getting to those extreme levels. And they do go to efforts as RS 103, where they have massive reverberation chambers. I mean, it's huge. They have mode stirs, and it's a very complicated and expensive process to get to those extreme levels of E fields and H fields. But with this, the advantage of this is I am injecting it directly into it without damaging it. This is a non-destructible method of finding vulnerabilities, and I'll get into how we do that on this thing. Okay, so computerized cars, medical devices, immunity, EMI was not sufficient. So again, the industry really looked at, okay, we need to cut down on how much is being rated. The other side to it, though, is I need to cut down on how susceptible I am to it. And that was certainly behind the curve. Rated emissions was at the forefront, and it's a little bit behind the times. So they actually started to repurpose some of the devices such as near-field scan imaging. The imaging was literally scanning over a surface, looking at, okay, what is my radiated emissions across this XYZ platform? And they mapped it out. You can see this is actually, this is a susceptibility plot, because as I'm going to get to, they repurposed this from the reciprocity theorem of antennas. What you're using to inject, you can actually, or what you're using to receive, you can use to inject. Transmit, receive, they can be interchangeable. So they actually repurposed this to now inject. Instead of measuring what's coming off of it, I'm forcing electromagnetic fields into the system. So they literally changed the term from scan imaging to scan immunity. And here, as you can see, they're actually plotting what is the relative susceptibility of that chip as they're tracing around in an XYZ coordinates. Like I said, the field of radiated susceptibility was developed quite a bit later than the radiated emission standards. There's certainly a gap in those standard testing, which is, again, why they're rewriting it. But what happens in the interim, right? Especially as we're going to DDGX platforms, it's going to be 100% electrically powered. This is going to be a major issue. And again, like I mentioned, our test bed enables non-destructive, pre- and post-compliance modern power electronics EMI to be injected into mission-critical devices under test. So what we're modeling, again, is the power electronic spectrum. So I'm looking at, we chose 1 meg to 100 megahertz, which is a very vulnerable point, obviously not captured in the mill standard either, and it simulates some of the radiated EMI that's coming off of power electronics. We were, in previous master's theses, we went through the whole process of proving that this causes failures in systems. Gate drive boards, we were throwing gate switching algorithms completely out of whack, and we were able to create failures. So, but my job was, well, how do we quantify exactly what H field, for instance, caused that failure? And that's where the modeling comes in. I need to tell you exactly how many amps per meter it would require to cause this failure, and then you can essentially predict what this system can put out and try to reach those levels, so you have a better understanding of how the system is quantitatively behaving. Okay, a few little basics. Like I said, kind of went over this already. Near field, though, we're right up on it in the near field. If you think of, like, say, a capacitor can have, very high voltage, but it's going to be low current because it's very high impedance. That's going to create a different type of field. And the H field you can also think of as very high current, low voltage. I mean, in my case, I have high current. It's literally short. The current is flowing through that core. It's creating an H field. But as you're in the near field, it's the actual geometry of the device that explains how much E field, how much capacitance, how much H field and current. That's very unique to the geometrical structure of the device in the near field. As soon as you get to the far field, which is the threshold is at lambda, or that's the wavelength frequency you're operating at over 2 pi, now you're actually getting a transverse electromagnetic propagating wave, where you know that the E field and the H field are actually orthogonal to each other and they're in phase. And then traveling through space, you can actually divide the two and get approximately 377 ohms. So it's the near field, let's just say, is quite nuanced. Okay. So far field, just like what I was saying, they are in phase, and they're approximately, the division of E divided by H is approximately 377 ohms as it's traveling through free space. And so this is a little diagram again here, just to kind of review what we were talking about with source, victim. So you can either have radiated or conducted emissions. I was purely looking at the radiated side, where it's actually propagating through free space off of a conductor. but there's also the conductive emission side that is still contained within the conductor. Now granted, some of that will actually radiate out also, but there's a whole other field of conductive emission EMI that is also very important to understand that Professor Reedy works directly on. But we're looking at more of the radiated emissions and radiated susceptibility side. Again, it's like a source and a victim. All right, so now we're on to the actual test bed. So I didn't actually bring the entire test bed in, but I brought up at least a little picture here to kind of give you a rough idea. Essentially, it's a couple of signal generators. You can see them on the top left there. A power amplifier, AR power amplifier, 100-watt power amplifier. I have an oscilloscope to essentially just look at the modulated waveform that I'm putting out that creates a non-destructive type of waveform to inject in the EUT. This EUT right here, you can see it's powered, so I'm actually testing it in an operational state.
That was one of the points.
Oh yes, I forgot about that. It's awesome. So right here, powering this DUT, and you can see we have a little H-field antenna right there that we're injecting some of this DMI into. All right. Some of the real basic principles. So Maxwell's equation has 4 laws. 2 of the laws are very applicable and we can leverage for this test bed, namely Faraday's law and Ampere's law. When I look at these 2 terms, I notice I have derivatives and I have flux values. The flux values are based on area, and they are essentially the top equation for Faraday's law is saying I have a changing flux through a surface area. Okay, and as my changing magnetic field in this case is changing through that surface area at higher rates, d by t, I get more or less EMI. So I can essentially, like I said, leverage these terms here. If I have a larger E or H field, they're kind of interchangeable here depending on what I'm using E or H. If I have larger E or H field, I'm going to create more EMI. If I have larger device center test flux loop size, I'm going to create more EMI. Do I have control over that? Absolutely not. The device center test is what it is. It's locked in stone. So I don't have, that's not one of my knobs I can turn. I certainly can turn the amplitude though, and I can change the frequency. Faster change in flux of my E and H field also produces more EMI. So that is what we leverage. And same thing, just showing here that the signal generator is essentially, you can see the 2 generators on the left, on the bottom side, I'm able to actually adjust that amplitude, adjust that frequency, and in doing so, adjust the amount of EMI that I'm injecting. This is actually patented as well because it is so powerful. It is a modulation technique that essentially makes what would be normally a continuous wave type sinusoid doing a lot of damage to systems not do damage to systems. And it's twofold. So if I look at signal generator 1, I'm creating this trapezoidal envelope. That trapezoidal envelope modulates a sine wave. Then that modulated sine wave is actually injected into the equipment under test. And again, signal generator 2, I'm increasing the amplitude and frequency to change the amount of EMI. Signal generator 1 is actually creating that modulated envelope. Well, what does the modulated envelope do? Like I said, it's twofold. I always kind of compare this to a flame. If someone lights a match and just really quickly brushes it against my skin, well, that's a very low duty cycle. It's not going to do much damage. I'm not going to feel much pain, right? But if I had a higher duty cycle, it was on for 100% of the period, you're going to feel pain. It's going to do a lot of damage. Continuous wave, for instance, that'll do a lot of damage. But when I modulate it to a duty cycle that's only 1%, it's like just an instantaneous pulse, and I find the vulnerability, back off, let it recover, it disperses the energy, right? So it is a low average power, high instantaneous power. The other, the second side of why this trapezoid is so effective is the slow rise time of the trapezoid. Everybody knows in your DSP classes, if you have a fast rising square wave or a quick edge, it's going to have many high frequency components in the frequency domain, right? Well, if I basically take that slope, I can cut down on higher order harmonics. So then what I'm injecting is exactly the frequency that I want to inject, not higher order harmonics I wasn't intending, and I know what to attribute to what. So it's, again, kind of twofold. Now the modeling I'm doing, just as a disclaimer, I'm doing this continuous wave instantaneous portion. which if I did not modulate it in the normal world and was using it, I would blow a lot of things up. It would be bad. H-field injector now. So Richard here has helped me build quite a few of these, and I don't know where Richard. There he is. There's the master H-field injector. So we've made plenty of them. We got small ones. We got, well, this is like 33 millimeter. We got 20.5 millimeter diameter. We got long length coax, short length coax. Notice these are not shielded though. Okay. This shield has the effect of essentially decoupling H field from E field. I can tone down, because again, I want to inject a very specific type of EMI. If I want to inject more differential mode type coupling, I'm going to inject my H field. If I want common mode, I'm going to try and go for E field. But I don't want, I want to attribute it all to as much differential mode as possible and know that it's from H field at the frequency that I want. And by shielding it, by essentially taking copper mesh around the loop and having a segmented portion so that the H field doesn't get canceled out completely. The H field definitely propagates very well still, and the E field attenuates drastically. And from the measurements, we took almost 20 dB down. You get a slight decrease in H field, but drastic in E field. So that's great. Now I have the controlled type of EMI that I want to inject. This is just a little cross section of the injector that Richard and I have been working on this whole manufacturing process for a bit with the 3-turn magnet wire. You got the copper mesh that I use for the shielding. I got the epoxy and fish paper, basically all insulators, and create that kind of structure, that hard structure where I can walk up on something and not worry about shorting it out to the device under test because it's all insulated. E-field injectors. So this is the other side of the coin. Like I said, it's more for the common mode type coupling. You can think of this, it's pretty interesting, as half of an air gapped capacitor. I have a plate that I'm basically sending charge to, pulling charge away, sending charge to, pulling charge away, as in my sinusoidal wave. Well, what happens when I send charge to the plate? It's either going to repel or attract a bunch of charge in all of the common circuitry that is in that power that's all referenced to the same chassis type of circuit. It's a mesh circuit. So that actually creates all of this unified charge all coming together to be attracted to that charge that's on the plate or repelled from it, depending on where you're at in the period of the sine wave. And it causes mostly common mode type coupling. So another type of coupling, again, we haven't seen the drastic effects of the E-field injector as we did with the H-field, which is why we really chose to focus deeper into the H-field. Here's a picture of us, again, injecting directly into a gate drive port to establish regions of susceptibility. This was the previous master's student that I was talking about. And there's 2 master's theses that actually came out of this. And this is, they're going around looking for these areas of susceptibility. It was kind of like that NFSI that I mentioned at the beginning. But this was the precursor to it because there's no modeling, and that was where we came in one. Okay, what kind of H-field, what kind of E-field can I expect at these user settings for my signal generator? As everybody knows, for Professor Reedy and Professor John's classes, you have a very specific switching algorithm for these power electronics. If you throw that switching algorithm off, say for the gate voltage, it causes everything to go out of whack, whether it's doing a basic DC to DC converter or inverter. It creates a lot of noise. It's bad. Well, as you can see here on the bottom, I'm so bad at this. Okay, so you can see here on the bottom, this is the actual trigger signal. That is that's actually triggered by the injection of that modulated trapezoid. You can see 200 microseconds later, all of a sudden my gate drive port sends out an optical fault. So it was very clearly attributed to the injection that I, or the master's students injected into that. Okay, so in order to do that, I kind of broke everything. I compartmentalized everything into every segment of an injector and of the test bed. Start off with just the antenna modeling. So I broke everything apart. I go like this one is, for instance, a 2-turn loop, and I had 3-turn loops. I basically was looking at all those characteristics of the antenna. Then what that gets connected to is a coax. So this is a tiny little coax here, a little 6-inch coax. But that's the next part that I needed to model, RG58 coax. Then I had to just model the actual signal generator. That signal generator could amplify the signal into the AR amplifier, which was the next step. I had to model the power amplifier, the 100 watt power amplifier. And then as a whole unit, then I'm able to model the actual full test bed. Again, we chose the range between 1 megahertz and 100 megahertz because this falls within the modern day power electronic EMI that is not really directly captured in the electrical standard, making this a very important into a few assumptions. I started off after I finished all my exams, I started off in an electromagnetic, advanced electromagnetic class and started to see, wow, I thought I understood Maxwell's equations pretty well. That was not even an appetizer for how crazy it gets. I mean, it's unbelievable. You're going to like Lagrange transformations just to deal with the math is just unbelievable. This is just this simple equation of a magnetic dipole. As you can see, there's just endless. There's derivatives. There's even there's new terms they introduced, such as retarded time or retarded voltage. And essentially, what that is it's the amount of time it takes the finite speed of light, electromagnetic wave, to travel from point A to point B. Because you can have a charge configuration, and I have a field at time t equals 0. Well, that field is that plus the amount of time that it's going to take to get here. So it's an aggregate. You're constantly summing up all of this field. It's extremely complex, and thankfully, I was talking with some of the physicists and Derek and everybody about some of these electrostatic and magnetostatic approximations that greatly simplify this. And we were really concerned, like, is it going to work? Is it going to work? So we started that whole mess up top. Basically can be brought down as long as these assumptions are correct. Brought down to a very simple kind of one term here. As long as the assumptions where I'm saying that the highest frequency that I'm working at is 100 megahertz, the wavelength of that is 3 meters. Well, 3 meters is much, much bigger than, say, for instance, this, right? So the assumption should hold. And so let's try it. That's Biot-Savart law for the current in a coil. And so in order to prove this, we again sort of around this coil here. So I could take a current clamp lent to me from one of my colleagues, and we were able to determine directly what that current was and plug that current into the Biot-Savart equation, then compare that to the voltage induced. So like for instance here, if I am injecting a certain or I have a field coming off this, I call this a sniffer. And so I'm actually sniffing it. It generates a voltage in the sniffer that I plug into that equation there, knowing the area and the frequency that I'm working at and all that good stuff. Yes. So they should be comparable, right? They're both measuring the H field around the loop coil. And one-term coil, look at the H field versus frequency here. Pretty decent overlap, and we felt confident enough to move forward with this. The H field measured by both should be a relatively good estimate. All right, so that was the assumptions that we had going in to use a lot to verify a lot of the modeling we're about to get into. So again, the first stage was the antenna. We know that an antenna, or I should say a loop, has these characteristics. I can know the radius of the loop, the diameter of, say, the 24 gauge magnetic wire that I have there. And as that radius changes, basically you can see it's directly proportional to inductance. The big R change, or the smaller changes, you get bigger L. So bigger diameter loop, more inductance, smaller, less inductance. And then obviously the amount of coils you have too. If I have, say, 3 turns, I'm going to have more inductance than just 1 turn. And I calculated these out and then actually started to go, and this is exactly, I would take port 1 of my VNA, do an S11 test, and essentially I was able to look at actually the Smith chart from this and determine what its actual inductance and capacitance were. And pretty close to the calculated, but I wanted to be a little bit more precise because I couldn't say that I precisely had, for instance, 20 millimeters all the way around. There's always going to be inconsistency. So I wanted to get a little bit more precision in what I was putting into my model. This is how I did that. Again, this is my VNA here, and I used a program named SimSmith. that is really cool. I can literally overlap a trace on a Smith chart, looking at its impedance across my frequency range, and overlap it with a mapped out circuit equivalent of what that should be. And so that helped a lot. And I was just kind of comparing and contrasting everything as accurate as I could with what was the inductance and capacitance. Obviously, if I have multiple terms, I'm going to have a bit of capacitance between the terms. But the capacitance was always relatively negligible, very small. So again, I took this from the Smith chart. I just looked at essentially far enough away from the self-resonant frequency. I got an accurate inductance looking at the Smith chart. Where it crossed the 0 degree mark is essentially where it's going from inductive to capacitive, and I was able to calculate the capacitance from that, from the just 1/√LC relationship, and plug these values in, and you can see here that the actual values the values that are here, right, are basically plugged in here and match all these. So everything was lining up. So now I knew what my antenna was going to be. Now, pretty straightforward was extremely far from straightforward. So the coax, I started off with something very straightforward, just a basic RLC type model, just a little second order RLC type circuit. Well, that definitely does not have the complexity needed to show some of the behavior that I was seeing in some of the measurements, such as standing waves here. You need to get in transmission line theory. You need to go into much more complex and cascaded type circuitry to look at what happens when you have a coax cable and you basically short it. That's exactly what I did here. I went from 50 ohms of my coax to 0 ohms. That's a horrible mismatch. It's going to cause standing waves. I'm certainly not going to be able to use a basic RLC type circuit, especially in the frequency range that I'm working at, to adequately model that. I started advancing, started moving along here. I had my pi type circuit through a couple of them in and improved the accuracy a bit, but not until I went to a pi type of about 100 was I finally able to see and overlap the exact coaxial behavior I was seeing with resonant frequencies, resonant impedances, and everything. And so once I got all that to completely overlap, I knew my coax now was finally sufficient. We had to look at the specs of an RG58, the resistance per length, inductance per length, capacitance per length, and cascade over 100 of these together to finally capture some of the standing wave behavior that was there. So that takes care of the coax portion. Now we're on to the signal generator portion. The signal generator portion, again, I'm just trying to inject the continuous wave portion of that modulated trapezoid. So what is that? Again, continuous wave, it's a sine wave. I'm literally using a sine wave generator in a simple circuit program like Plex. But what was a bit of a challenge for a bit, until Professor John pointed out, it's like, oh, you need a 50 ohm in there. And as soon as you put that 50 ohm in there, you notice that you're essentially getting a voltage divider at the output that's feeding into your coaxial cable. So if I'm going to go, say, 900 volts VP, I'm only going to get like 450 volts at the input to my injector. And so having that 50 ohm in there and realizing that it's in essence a voltage divider, even with a short at the end of it, was critical in understanding. Okay, so here's the whole setup. This is the whole deal here. Now this is actually modeling the AR amplifier. Okay, so I needed to look at, I did the signal generator, now I'm looking at how is the AR amplifier behaving with this horrible mismatched load that I'm putting on it, such as an injector. And in order to do that, you can see here I plugged port 1, so basically injecting a signal. In a VNA, just real quick, you can think of port 1 as a signal generator, you can think of port 2 as a spectrum analyzer. And essentially I am injecting from port 1 a signal into the input of the AR, and then the AR is amplifying that. The output of that AR then is looked at from the spectrum analyzer side of port 2 of my VNA, and I'm able to then use some of all that data to begin to model how the AR is behaving across our band. This is a 100-watt AR amplifier, which obviously very, very quickly when I started adding the amplifier, I started realizing, wow, we need to be careful. We're not using the modulated trapezoid we could do some serious damage here. And I was getting, unless I was very instantaneously taking data and turning things off, let's just say these guys can heat up pretty quick. They heat up real quick. And so it's some funny smells and some, didn't let the smoke out completely, but yeah.
The varnish of the wire.
Yeah, the wire got a little,
The varnish.
little toasty, yeah. But it was all in good shape. So in order to compensate for this super high power, I had to call in another friend and get what is called a coupler. So this essentially makes it so it's very safe. I can look at what's on the forward line of the transmission line, pull that off at negative 40 dB down to feed it into my VNA without blowing out my VNA. Because I couldn't take these measurements just straight raw. I would blow this out completely. 20 ppm is the max this guy can take it for too. So I had to cut it way down. I had to use a lot of attenuators. I had to do a lot of different things to protect. I had to use 100 watt resistors. And in this case, as I have this 100 watt 50 ohm resistor on the end, you can see, look at that nice plot of gain versus frequency. When I have a 50 ohm load on there, it's almost perfectly flat across the spectrum. And what happens when we put my injector loads on it? Again, standing waves. I get some of this behavior, it's a horrible mismatch. But it is impressive. The AR, as they claim, it is an absolute tank. And it can handle viswars that are just outrageous, still power it, not damage it. The reflected wave is coming back right into that output and somehow not doing any damage, ever. And they're very proud of that. So, like I said, one of the AR manufacturers lent this to me. It's like $3,000, so it's really nice of them. Didn't want to buy it out. So, like I said, I needed to add this behavior to my model now. I'm not just going to get a flat gain plot versus frequency. I'm going to have some waves, and that's exactly what I did. I added that delta from my 50 ohm to the actual model to complete the overall test bed circuit model. So you can see here I have a single generator, my AR amplifier with the gain there, the coax, the coax we talked about, and the antenna with all the Sim-Smith chart and calculations and measurement we did on there. And in the end, we started, as you can see here, I got a cool little cartoon of an HFSS H-field injector that every one of these is built from 100% scratch. Like you literally start with a center conductor, then you build a polyethylene on it, then you build the outer jacket, the shield. The entire thing is made from scratch. And all the dimensions, all the permeability, all of that goes into this modeling. It's extremely impressive, and it can actually tell you what H-field to expect depending on what you're injecting into the system. So HFSS stands for High Frequency Structure Simulator. And it's actually very similar to like SolidWorks, but SolidWorks is more from like a mechanical standpoint where you're mechanically loading, you're and stressing things in the mechanical realm, whereas I'm stressing it in the electrical realm. I'm looking at the propagating electromagnetics coming off that. So I'm able to make extreme parameter changes and see kind of what to expect from HFSS. Very powerful tool. And this is actually our latest stage here. You can see I got my sniffer set up, and in this case, I built it so that I can literally change every parameter. I can go from 1 coil, 2 coil, 3 coil, 1 foot long, 20 foot long coax. I can go from any diameter I want, all which is at a click of a button. I can do all of that. And then I'm able to couple through to my sniffer and see exactly what I should expect to measure in my field here. And you can just see here, one of this is decibels of H field, another one is just absolute meter. And again, we simulated it from 1 megahertz to 100 megahertz. Here's the results. So this is back to the equivalent circuit model. This is the road that we focused on at first. As you can see here, very nice overlap. This is at an AR of 0% gain. This is with my free turn coil. At most, it's off by 0.35 dB from the model to measured. So the green here is my Plex model, as in the Plex circuit model. The blue is measured. So I can tell you within very good accuracy what to expect at whatever frequency and at whatever amplitude that you were setting the system to. And then here's the same setup with 50% gain on my AR. You can see very nice overlap. Worst case is 0.36 dB and 100% here. I would say that the 100% does get a little bit noisy. You can kind of see some of the noise in some of these curves here, but still my model held together very well, even operating at those high levels. For a one turn, again, we did tons of combinations and permutations of length, diameter, coil number, but this is, for instance, a full run of one turn at 0% gain. 0.49 dB was the max this guy was off. This was 0.44 dB at 50% gain. Again, this is H field versus frequency, so I can predict what your H field is at whatever frequency before you even turn it on. Just tell me what the frequency is and what your signal generator is going to be, and I'll tell you what your H field is going to be. And here's the one turn at 100% gain. Again, you can kind of see the noise starts getting a little interesting, and it held. And then here's another, just to confirm what we spoke of earlier with the H field and the shielded injector. You do lose about, say, 2 dB in the shielded of H field. However, I lose 20 dB of E field. Remember, that was the whole decoupling purpose. I was trying to decouple the E field from the H field so that I got more differential mode type coupling. And you can see here, measurements show very effective. It works very well. And Richard and I have been building quite a few of these. It's no joke. Sometimes you could accidentally solder and heat things a little bit too much, and things become interesting. But you can see here too that the unshielded grain trace. You see how much noisier that is? Well, the blue shielded trace actually, it certainly acts as a bit of a dampener on any of these resonances that are happening. You can see how much cleaner that trace is with the blue. Just get to some of the HFSS results. So again, so many lessons learned from the original equivalent circuit development, understanding all the parameters that really affect what my H field is going to be. So I needed to make sure that those parameters at least lined up to do a sanity check. Visual checks, Smith chart checks with scattering parameters S11, my impedance versus frequency. These are all parameters that I was checking to make sure everything was set up correctly and that I was actually modeling the same scenario. You can see here on the bottom, this is my HFSS 3-turn coil. That's like 33 millimeter diameter. I got my 11 millimeter and my 20.5 millimeter up on the top there. Again, unshielded, and I can also do the shielding as well in HFSS. And it's really cool. It shows essentially that same cut down of the E field, drastic cut down of the E field. I just put in the parameters that it is copper, for instance. I put in the basic permeability of standard copper, and it cuts down as expected. And here's the overlap of measured versus H field. So you can see here on the top, that's my measure with the sniffer, and on the bottom is my H field. Very nice, only like 0.8 dB error across that. And again, I can rapidly confirm the effects of all these different combinations and permutations of loop size, diameter, coax, etc. So it's very powerful. There's a lot of different injectors, epoxying them, shielding them, shortening them, lengthening them, and we wanted to see if there was any of this information we could use to leverage from a user standpoint, right? Because somebody in the end of the day has got to use this, and they want to know, okay, I got to inject this type of H field into this type of system. What would you recommend? So that's what we put together. So here's some of the things in the user recommendations that we're going to go over real quick. Here, the actual gain setting, the signal generator amplitude and frequency setting. Remember, those are the two knobs that they can turn to increase or decrease EMI. And then my H field injector loop number and size. That inductance obviously affects things drastically as well. And then the shielded versus unshielded. So for the just general feedback on the AR amplifier, what's interesting is you get to that 90% mark on the AR amplifier, and you go another 10% to your 100%, and you get like 0.1 dB. So it's quite negligible. It's good to know though, as when you're walking into this blindfolded. We had to back out what all these actual dB values were, because all that you have on the AR front is literally a percentage knob. So what is that? I knew that the max it could put out was 54-ish dB, and it was 100 watt capable, but I needed to precisely know what those dBs were. So we mapped that all out, and we recommend to essentially set this at around 80%. That's where you're getting your most bang for the buck. Set it at 80%, and then actually use your signal generator to change the overall H field you're putting out. So I'm holding the amplification the same, I'm changing everything with the signal generator. I also need to remember that I can only put in 630 millivolts peak to peak, which is 1 milliwatt, into the input of my AR, or I'll blow it out. I can't say that. Again, they're tanks, right? So they know people are going to put a lot more than that into it, but they don't recommend exceeding that. So you knew that 630 millivolts peak to peak was our max single generator input we could put into the AR. And you can see here, peak to peak, and you can see that the measure points in the little blue dots here in my model, very nicely overlapping again. And I can tell you, again, at say 1 megahertz, that I'm about 71.7 amps per meter in H-field. And at 100 megahertz, I'm about 15 amps per meter. And that was at 100, so then I went up to 500. Remember, the max is 630 millivolts peak to peak. I'm holding my AR constant at 80%. And you can see here again, very nice overlap with the measure to model here. All the way up to 337 at 1 megahertz, and 100 megahertz is 57. Notice what a drastic slope that is, though, versus frequency, right? That's quite a negative slope. So in using this from a user standpoint, you've got to realize, okay, when I'm really low frequency, I'm going to get quite a lot higher H field than I am if I'm going higher frequency. It's going to drop off drastically. So that'll come into play. So some of the things, again, we went into this loop size discussion earlier and its effect. Loop size and number of coils effect on inductance here. So again, increase the diameter, more inductance, increase the number of coils, more inductance. But is there a trade-off there? Is there a trade-off? Obviously, more inductance might do something. Well, from Professor Sharif's class, I knew quite a lot about cutoff frequencies and getting to that negative 20 dB per decade section of your transfer function. And certainly with the 3-turn coil at a higher inductance, right? We knew the 3 turns going to have more inductance. So that cutoff frequency is going to actually happen at a much lower frequency. You can see here, as I talk this out, I literally...
Exercise. Exercise. Exercise.
Swim.
It's a good thing that was just an exercise. 7 times more on the left. If I go the axis, H field, 18 to 6, 12 delta, 35 to negative 5, that's 40. So I've dropped 40 across 100 megahertz with a 3 coil. So I'm deeply into cutoff realm with the 3 coil, but not so much. I can hold that H field a lot more constant if I just have less inductance, if I have just 1 coil. I think this battery might have died, sir. It's not going to need it now. I got the white one.
Rob,
Actually, let's go
does
back to
the
your...
orientation of your sniffer have anything to do with?
Oh yeah, I mean obviously, yeah. If I'm not getting the same flux through it, if I come off with the sniffer that's at an orthogonal angle to it, I'm going to get much less.
Rotations around.
No, rotation around it is noticed, but certainly as I come off angles, you're dropping off quite a bit. But again, I'm trying to simulate the scenario where I'm right up on the EUT. I'm like pressing my injector right into the system. So that would be the sniffer type scenario that I'd be setting up. I'm pressing the sniffer right up against that insulated layer. So I'm getting to like 0.1 millimeter. So very little attenuation through the separation between the two. But let me see if I can get this slide thing. Yeah. Okay. Charged. So here again, shielded versus unshielded. 20 dB attenuation of E field. I would say that there's little advantage to not having a shielded system, other than when you're doing a 3 coil and you're soldering, like I was mentioning with the originator, it's a lot more difficult to solder when you have 3 coil. You can literally melt the coils together. So that's kind of one of the only downsides I can think of when you're using the shielding. The shielding is very effective. It cleans up your trace. But it is, the manufacturing process of doing it is not easy. It's, you need to essentially spot solder it and create a very unique little insulation section. It's not easy, but I think that it's worth doing because of the effects. I mean, I can totally decouple my E field from my H field and clean up the signal as well. gain versus frequency on my AR. Again, look at the shielded. Look how clean that green is. Look at the unshielded. It's just, it's noisy. And there's that dampener no longer there, right? There's a slight peak shift because you're essentially kind of changing the inductance when you add some of this shielding. But, okay, here we are. So this is a industry expert from NOCAD EMI out of Pax River. It's all he does is EMI, EMC testing, more on the avionics side. And I had a long conversation with him. He was totally okay with me quoting him and putting this up as our conclusion, because I think it kind of hits point home. The EMC EMI testbed would be a huge asset for pre-compliance testing before an equipment under test is brought to full mill standard 461G testing. According to Mr. Lawrence, no such pre-compliance test is currently used by Navigator testing or their affiliates to minimize the troubleshooting and time spent under the costly umbrella of mill standard 461G testing rates. Now, by no means am I saying ditch 461G. I'm saying this is a pre-compliance, post-compliance solution that adds so much knowledge to what your vulnerabilities are before you go to full manufacturing. You put these out in the field, and all of a sudden, you know, you're having all these issues that 461G said you should be good about. Well, the EMI environment has kind of changed in those few years, you know, so it's always good to do some sanity checks in-house and find vulnerability yourself. Plus, if you're in the middle of taking, for instance, or making prototypes, you can adjust some of these characteristics of your circuit board layout, et cetera, you know, bigger traces, more flux, smaller traces. There's a lot of things you can adjust to hopefully minimize the effects of these shielding, filtering, hardening your system. There's a lot of things you can do. It's good to know before it leaves house. And even past this 461G testing, if you think you've got the whole on be gone, well, maybe not so much when it's on one of these destroyers with all that electromagnetic interference. Here's some of our publications. So we presented and published in a conference in Phoenix, Arizona with Professor Jan and Professor Reedy. And then we are submitting now, hopefully by the end of this month, which is coming up pretty quick, to IEEE transactions. We're confident that, especially with all the HFSS circuiting or modeling that is working, as well as all the equivalent circuit modeling we have done, I think this is a huge insight into what this test bed is capable of. And from the last briefing of OMR, it sounded like there was people who were very interested already in using this and moving forward with helping the Navy avoid issues before it's too late and deploying a bunch of stuff in the field that 461G said is good to go. Okay, so future works. I keep going back to this. I know Professor Reedy is very busy, but I just think it would be so cool in the conducted emission testing that she's doing to show that, okay, when in order to improve some of the conducted emissions, she's actually increasing or decreasing inductance in circuits. She's balancing circuits. There's all these different elements that are being added to the circuit to cut down on conductive EMI. What's the trade-off in the radiated side? So now I add more capacitance. Is that more common mode coupling? I add more inductance. Is that more differential mode coupling? Until you look at both sides of the coin, what's the trade-off? You could have improved conductive emissions, and hopefully it's a win-win. You improve conductive emissions and you improve conductive susceptibility and radiated susceptibility. But you don't know until you tested it. I think it'd be a very fascinating master's thesis to go. There's a few other certainly use a little more investigating, like the RF pin injection tool that it actually forcefully injects EMI directly into pins on circuit boards. That would be a much, I think, simpler modeling process. We already kind of have the circuit schematic of it, but really honed in a lot more on the H field. Now the E field electrostatic approximation, I never really got. We started off doing both, the E field and the H field. The E field, the electrostatic approximations. The problem is when I'm making these measurements, when I have an E field measurement I'm trying to take, now all of a sudden my capacity, my body's capacitance, creates a ton of background noise. Pulling the signal out of that noise is not easy, especially when my whole body is acting as a massive capacitor that's nearby. And so a lot of the data we're having, that was the toughest part. Is, again, some of those electrostatic approximations and showing that my measured data is lining up. So that would be something certainly to investigate a method for doing that, for not introducing so much capacitance and noise into the measurements. And then there's just so much, now that their HFSS model is working, there's so much you can do in that realm. I mean, you can change every parameter you can think of at a click of a button. And you're able to see what kind of effect that's going to have on your H field and E field propagation on everything. So it is extremely powerful, and I can see why it is the industry standard, HFSS. CST is one, and HFSS is one of the others. And it is very impressive. Certainly not very user-friendly, but very impressive. A lot of hotkeys and menus. So, any questions? That's you guys right there.
Assuming the quote you put up from, who was it, Steve Lawrence?
Yeah, from Knockout.
Assuming that's correct, is once people are more aware of your results here, are they going to want to be building these systems? And is there going to be a demand for you to start a new company or something, making these probes and putting together test
I certainly have some ideas. Yeah. I mean, for starters, let's get a little bit of better impedance matching, right?
Yeah.
50 ohms to a short is probably not that good of an idea. So there's a lot of improvements that can be made on it, but I think it already, as it stands, it's filling such a void. And like we said, we just had that briefing with O&R, and they're very interested already. Because you can use this right now. We know what H-field to expect. We know how to create failures. And it's ready to use. And we put that out there at O&R. So this has been an absolutely fascinating topic. I kind of come from a field very similar to this, and it just has been really challenging, but at the same time, it just brings in so many different types of electrical
So
engineering.
the issue, though, is that it sounds to me, not being in this area of specialty, but it sounds to me like a big contribution that is going to be actually used by Navy labs and Air Force labs and eventually commercial applications.
Yeah.
And the issue is, you built your own, I mean, you assembled your test bed from off-the-shelf equipment except for your probes.
Right, and that's
But
custom hand.
Everybody now is going to have to go build those probes from scratch.
We'll have to talk to Richard.
Yeah.
There's a lot of small companies that are already doing that.
Yeah.
They're making these kind of
But
probes?
they keep them in-house, like it's, company.
They're all there's little people, if you go online, you can see people are trying. They're all trying to push them. But that NFSI one is the closest one that I can see, but it doesn't have this non-destructive modulation property where I can see your vulnerability without damaging. I can get to such a high level. There's actually temp cells too. You can get to very high levels, but again, none of it is able to do the testing without damaging your equipment under test and still exposing the vulnerabilities. I get to very high levels without affecting your operations. There's a lot of applications of this. So I think as long as it's presented to the people that could make use of it, that are currently, like I said, this guy's been doing it for close to 30 years now. That's when I talked to him at the beginning, and he's really impressed with how far we've come, and that's at Pax River. So they do all they call the EQ testing on avionics there, all the EMI, EMC that's on board with airplanes, and good times, right?
Yeah.
Actually, that's really close to home because about 20 years ago, I spent a lot of time in the anechoic chamber.
Yeah.
We put a new ALR95 V2 ESM system on the P3, and the fleet found out there was an artifact from the system that was getting picked up on the acoustic racks. And so what do you think they did when they went out on the station to go track submarines?
Yeah.
They turned it off, and it's a really good system.
Right.
And so then we had to figure out how to shield it, and spent so many hours in the anechoic chamber.
Yeah.
But this is after the fact, so if the contractor had been able to test that in the lab before we installed it.
And then that's no longer an acoustic data that you're gathering. It's a purely electric. I mean, I just on the whole grams thing, I've seen plenty of artifacts on grams too. There's just it's purely electric. It was not an acoustic signature, and it was all an in-house EMI type coupling that was providing, in some cases, across the spectrum. We had a grounding issue at the facility I used to run that it was bleeding over into everything, and it was purely our site, nothing to do with the external acoustic environment. So,
Yeah, if you maybe a few years ago when they're doing laboratory ships, and they have the power generating is basically the 777 engine in there to generate power. one of the missions for the littoral ship was to do anti-submarine warfare. The noise and I bet it's that keep coming out from the generator.
Yeah.
Completely prevented people from doing ASW with that. They even took that mission part of the littoral ship out. Being the anti-submarine said, no, that's not our mission. Our mission will do other things because we could not
operate with them. Well, that's why you get into the whole realm of shielding, filtering. There's a lot you can do to still be able to operate with these extremely noisy, whatever it is, in your work environment. But that's a whole other specialized field that is also very interesting. But yeah, you need to handle it because it ruins the functionality of everything in this environment. It's bad electromagnetic compatibility.
Yeah. So they didn't check that before even we doing the design.
Right.
We go with that. Should we try? And they said that if we use the 757 engine rather than the 777 engine,
right?
The General Electric was making, maybe we would have. So they needed.
Yeah.
To try to test that.
Yeah. There's a lot of things make it through the cracks. They're fine by themselves, but you start throwing them all together in one room. What's going to happen now? So that's why the susceptibility side is so important, right? I just have to assume everybody's going to put off the worst electromagnetic environment I can imagine. How can I make myself less susceptible to that? And that gets into the whole idea of shielding, filtering. There's a lot of methods you can use, but if you're not aware of it, things are going to fail.
So I'm reminded.